All right, we are live on YouTube now, so thank you for your patience. We're still trying to work out the bugs with how to do this. So I've had to get Bobby's help to reinitialize the whole live stream feed. So the advantage with the YouTube stream is that this whole session will be recorded by YouTube, and you can go back and rewatch this one at any time that you want, or you can watch any of the other trainings that I've done or that we've done in the facility to try to learn more or maybe catch some things that you missed. So feel free to use that resource. All right, so we're going to get started with the loading and unloading a sample. That's going to be the first process of using the Nova. And actually, let me back up. The first thing I'm going to do is I'm just going to point the webcam at the microscope, and I'm just going to go over some of the big components of the microscope itself, and then we'll vent the chamber and load a sample. So let me expand the webcam screen here a little bit. Where's the best spot to stand? I guess over here. All right, so this is the Nova microscope itself. So the main components of this system are the vacuum chamber, which is this big, large, boxy thing right here, and then the electron column, which is the vertical column on top of the vacuum chamber, and then the ion column, or the focused ion beam microscope, which is this column right here. This is a dual beam microscope, which means that we can use the electron beam and the focused ion beam at the same time, which is very useful if you're doing fib work to cut samples. You can monitor what you're doing with the SEM images while you're cutting with the fib. There are a variety of accessories on this tool that are used for doing fib preparation mainly. On the front here, this thing is called the OmniProbe manipulator. This is a very sharp tungsten needle that is insertable, and you can move it around and use it to probe your sample or pick up objects on a sample, transfer them to somewhere else. This is used very frequently for doing lift outs, either for TEM preparation or atom probe preparation. On the front here is the stage motor controls. So this stage can accommodate a 2-inch diameter sample, a 2-inch silicon wafer or something equivalent, or several smaller samples as long as they fit within the 2-inch diameter circle. And it has the ability to move in X, Y, Z, tilt, and rotation. 4 of the stage axes have knobs connected to the motors, which allows you to directly move those if you want to by turning these knobs. And I'm not going to really use those today. I'll demonstrate how they work, but the main knob that is used is the Z knob, and that's mainly used for fib applications. Typically, we drive this stage around using the software. It's much more convenient. I'm going to pick up the webcam for a second. Pardon the shakiness. And if we go around behind the tool, on the back side here, we can see that there are 2 gas injector assemblies on this microscope. The gas injectors are used for the fib applications for depositing material on your sample. The 2 gas chemistries we have on the Nova are carbon on the lower injector and platinum on the upper injector. So on the inside of the chamber, there's little injection needles that flow gas right onto the surface of your sample. We also have an X-ray detector. This one is made by EDAX. It's a little bit older, but it still functions just fine. The X-ray detector is also referred to as energy dispersive spectroscopy, or EDS, and this is used to collect the X-rays that are generated from your sample when the electron beam hits it. And we can use this for doing chemical analysis, elemental mapping, point analysis, things like that. Now, I am going to be hosting a brief, well, it's 2 hours approximately, but I consider that fairly brief. But I'll be hosting an EDS training for this microscope on Monday that will be on this YouTube live channel. So if any of you want to see how the EDS system works on the Nova, I would suggest you tune into that or watch it, after the fact. It'll be archived. So those are the main accessories on the Nova. The other side of the chamber, just to show you, there's really nothing over here. There's a large port on this side, which if you go to other labs, they frequently would have some kind of a load lock system that would mount here. If you come to our lab and use the Helios 650, we have a load lock mounted on this port. On the back side of the chamber, hopefully you can still hear me, is just some of the feed-throughs and electronics for the system. This large blocky thing right here is the amplifier for the electron detectors, and everything else is just pumps and things. These guys up here are ion pumps that keep the column at high vacuum. There's a couple pneumatic controlled valves that open and shut when you turn the electron beam on and off. On this front right here, there is a mechanical aperture right here. I don't recommend that users in our lab ever move this. It is possible to change this aperture to various size holes, but we currently have the aperture set up in the highest resolution condition for the microscope, and the only reason you would ever need to change that aperture would be to go and get more beam current for doing EDS. However, I think that there's plenty of beam current available even with that high resolution aperture setup, and there's really no reason for you guys to ever mess around with this. So I just want to caution you, if you read the user manual for the Nova, you might find sections that talk about adjusting the aperture. Please don't do that. Please leave that alone. We're going to do all of our alignments within the software. We're not going to move anything mechanically on this tool. So when you come in to use the system, you should hopefully find that the chamber is under high vacuum. We want the users to always leave the chamber pumped down when they're done. So when you come in, and if you find the system is vented and open, now that's a problem. It would be nice to let me know or let Bobby know so we can remind the previous user that they messed something up. But first thing we're going to have to do is vent the chamber. Now this process takes about 3 or 4 minutes usually. So if you just need a minute or so to get your sample ready, I would recommend you vent the chamber and then prepare your sample to load it. That will be very time efficient. However, if you're going to need 15 or 20 minutes to prepare a sample, like say you have to put powders onto a tape or use silver paint, glue things down where the paint's going to take a while to dry, I would prepare your sample and then come vent the chamber. We really don't want to have this chamber open longer than we need to, because the longer it's open, the more dust will go into the chamber, the more potential contamination will get in there. So the best practices would be to open the door, put your sample in, adjust the height, close the door right away and hit pump. With practice and once you're comfortable using this, that's going to take you maybe 30 seconds to a minute to load your samples and close the door again. So you're going to see during this training session, we're going to have the door open for quite a while because I need to talk through all the procedures about how to load the sample. But just try to keep that in mind. Shorter times are better. However, don't rush. I don't want to see you panicking and rushing to try to get it in as quick as possible, because that leads to mistakes, and mistakes on these microscopes are expensive. So just keep in mind, we don't want to leave the chamber open. Don't go down the hall for 10 minutes to prepare a sample while it's vented. All right, so I'm going to switch up the view here so you can see the user interface, and we'll talk a little bit about how the user interface is laid out and where the buttons are to control the system venting. All right. Move the microphone. And let's see, I got to hide the webcam. Okay, so this is the user interface for the system, and it consists of a couple main areas. You have these 4 image quadrants that are used to display signals from the microscope. For example, the electron beam image or the focused ion beam image or the chamber camera, the CCD camera. On the top of the user interface, there's some drop-down menus and then a series of shortcut buttons that we refer to as the toolbar. These buttons allow you to change various conditions on the microscope, for example, accelerating voltage, scan speed, image resolution, things like that. And then on the right-hand side of the user interface is what we call the panel. And the panel is subdivided into 7 distinct tabs. Each one of these tabs has a name associated with it, and if you click on them, you will see that there are different functions buried underneath each tab. For example, if I go to the image processing tab, this is where we would go to perform measurements. There's tools like a ruler or measurements, things like that. You can also do image enhancements. It's like a crude Photoshop kind of thing. So as we go through training here, I'll talk about a lot of these tabs and their functions, but where we want to go to vent the microscope is the very first tab on the left. It's called beam control. And if you notice, if I leave the mouse over an icon for a few seconds, the name will pop up of that icon, which is very helpful. If you're not sure what those icons are and you need to reference back to like the user manual or something, just hover the mouse over for a second and the name will pop up. So we're going to go to the beam control tab. And at the top of beam control is the vacuum control area. So there's 2 buttons here, the pump button and the vent button. Hopefully those are pretty self-explanatory. The system is currently pumped, which is why it's disabled. So we're going to click on the vent button, and that will start the system venting. So I click vent, and you have to acknowledge this second message just to make sure you don't accidentally vent the chamber, and we say yes. Now the software is interlocked very well. So if you hit the vent button and the electron beam is still active or the fib is still active, the user interface will take whatever steps are necessary to protect the microscope before it starts venting. It is still a good habit to safely shut down and turn off all of the beams and accessories that you're using before you hit vent, but try not to worry too much that you're going to damage anything. You can have everything in operation and hit vent, and it won't hurt the microscope. The software will take care of everything it needs to. So this will take a moment to finish venting. While it's venting, we can, let's take a look at this bottom icon down here. There's this little colored icon that right now has 3 areas to it. There's 2 green rectangles, which represent the electron column and the fib column vacuum levels. And then the big orange spot represents the chamber vacuum. If all 3 of those icons are bright green, it means that you have suitably good vacuum in those areas of the microscope and you can operate the system. If one of those areas is orange, it means that it's either pumping or venting, so it's changing state. And we can see that right now the chamber area is orange because it's currently in the venting cycle. Those will eventually turn gray. Gray means that the system is fully, or that area of the system is fully vented. If you come in to use this microscope and you find that one of those areas is not green, you will not be able to operate the Nova. And that does happen occasionally. We might have like a power outage or some problem with the vacuum pump. It seems to happen especially on the weekends or in the middle of the night when there's no one here to help. But if you come in and you see one of those areas is orange or gray, there's not a whole lot you can do as a user. You're just going to have to send me or Bobby a message, tell us there's something wrong, and we'll fix it as soon as we can. But all 3 have to be green to operate the tool. Now, nothing on the software is going to pop up and tell us when the chamber is actually vented. What we want to do is just wait a minute or 2 and then go pull on the door. And if the door rolls open, then we know the chamber is vented. If the door doesn't open, then it's still under vacuum. But there will be no status message that's going to show up on the computer to tell us when we can load. So while we're waiting for that to finish, I'm going to reposition my camera and microphone again, and we'll go over and load our samples. All right, so if I think the chamber is vented, I'm just going to grasp the handle on the door and just pull on it gently, and you see that the door wheels open very easily. Obviously, that means the chamber is vented. If it's under vacuum, even a very small vacuum level, because there's so much surface area on this door, you won't be able to open it. So it'll either open very easily like this or it won't. As you roll the door open, go nice and slow until you hit the door stop, which is right about there. If you pull this door open extremely quickly, you can actually shake some alignments loose on the stage, and that can cause some problems, especially for the FIB user. So just go nice and slow. You shouldn't feel any major resistance until it stops. And where it stops, just so you can see this, is this handle is almost even with the front of this counter when the door is all the way open. So now that the door is open, let me move the camera again, and let's take a look at the stage. Let me see if I can get this a little closer. So this whole assembly right here attached to the door is the Microscope Stage. Again, I mentioned earlier, it's a 5-axis stage. It can accommodate a 2-inch diameter sample in X and Y, and it can accommodate a sample that's reasonably tall. As long as it can kind of fit in a space about here, it will work. In order to hold on to our samples, we use a stage adapter, which is this part right here. We have a variety of these adapters in the lab, and they tend to walk around a little bit. Usually this adapter is going to be with the Nova, but any of the adapters that fit on the other FEI or Thermo Fisher tools, so the Helios 650 or the Helios Plasma Fib, any of those adapters will also fit into the Nova and vice versa. So if for some reason you have a sample of like special types of samples, like say a TEM grid or a very, very short or very tall sample, something like that, we have some adapters that are probably with the other microscopes that maybe will be more suitable than this one. This adapter works very well for small SEM stubs, which is sort of the conventional way to hold samples in our lab. But if you ever find that you have more challenging geometries to hold on to, come talk to us and we'll try to find the best solution for that. Now, before I touch anything in the microscope chamber, I want to make sure I have a clean pair of gloves on. Now, I've been wearing these gloves all morning to protect my hands because of the coronavirus problem. So I'm going to assume that the surfaces of these gloves are dirty or at least oily. And if I touch anything inside this chamber, I risk potentially transferring that oil to these surfaces. And hydrocarbons and oil are our biggest contamination enemy for SEM. They will cause problems with imaging, especially when you try to do high resolution imaging of anything smaller than about 100 nanometers. If there's oil contamination in the microscope, it's really bad. We should always have clean gloves by every microscope in our facility, and we have plenty of more extra gloves. So in this lab, if you kind of look over here, behind there's a desk back there, we have boxes of gloves that are free to use. I encourage you to change your gloves often, especially every time you load or unload a sample, you want to put a clean pair of gloves on. I really don't care if you use 10 pairs of gloves in a day while you're working in our lab. I think it's a reasonable cost for keeping the microscopes clean. So please don't worry about that. So I'm going to go put on a different pair of gloves because, again, I think these are kind of dirty, and I will be right back. And you can probably hear in the microphone that the venting process is still going. You can hear the gas coming out of the chamber. That will stop after a few minutes, and it'll get much quieter in the room. But typically when you're loading samples for your own purposes, you're going to have the sample loaded and you'll close the door long before that process times out. So don't worry about that. You don't have to wait for that to stop. Once we close the door and hit that vacuum pump button, it'll stop automatically. Now the stage adapters right here, these are removable and they're height adjustable. And the way that we can adjust them by height or remove them is to first loosen this locking cone nut at the base of the adapter. And to do that, we simply grasp it with 2 fingers. And I'm also going to hold on to the rotation plate of the stage because this will actually spin if you put some torque on it. So I like to just hold on to that with one hand and then turn the adapter counterclockwise, or sorry, turn the cone nut counterclockwise to loosen it. That unlocks the adapter, and now I can either raise the adapter by turning it counterclockwise, which makes it taller, or I can turn it clockwise to make it shorter. If I need to remove it for some reason, I just keep turning it counterclockwise until it comes free. And this bolt is rather long. Eventually it'll come out. There we go. Right, so this is this adapter. Again, it's got the cone nut on it, which is used to lock it to the rotation plate. It's got the single threaded base, which screws into this large hole on the rotation plate. And then on the top here, it has holes for your SEM stubs. So this will hold 5 SEM stubs that go in these big holes, like one here, 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 and here. And then there are set screws around the perimeter that you use to tighten and lock the SEM stubs in place. The center hole, there's a set screw right here on the side. When you're not using any of these adapters, so I mentioned there's other ones in the lab, they should be stored in some kind of container that keeps dust off of them. In the Nova room, there is a white plastic box. There's a white plastic kit that sits over on the desk, and I would like you to store any adapters in there while they're not being used. If you're using the Helios 650, there is a desiccator cabinet on the desk for parts in that lab. We should also have tools available for loading and unloading samples. So there's a plastic tray right here, which should always have a small wrench for tightening the set screws, and it should have the height gauge for measuring the height of your samples once they're loaded. We usually have a set of these stub tweezers sitting by every microscope as well, but unfortunately these tend to walk around the lab, so if you need a set of these and they're not right here, I would go check with one of the other microscopes. You know, it seems like the SEMs, the Mira 3 or the Rise, those users tend to grab them a lot. I'm not pointing fingers, but they tend to always be over there. But you can just look around at the other systems or the other fibs and find a pair of those if you need them. All right, so we're going to put this stage adapter back on. So to put it back, we're just going to turn the screw into that center bolt hole and tighten it a few turns. And at this point, don't worry about getting this at any specific height, and don't worry about locking the cone nut. You're going to have to be able to spin this around in order to load your samples. So if you secure it, you're going to give yourself problems. So now what I'm going to do is I have 2 samples I'm going to put in. These are just some like easy samples I like to use for training. One of them is a spark plug tip from a car engine. So it's a platinum surface with little carbon nanoparticles all over it from the combustion process. And then the other sample I'm going to put in today is a burned out filament from a light bulb. So it's just like a tungsten spring or tungsten coil. And it has all kinds of little nano, I think they're tungsten oxide or some kind of little nano tungsten particles all over it. Both of these samples are pretty easy to image compared to what a lot of the users actually bring in. But this training is just to kind of show the basics of the process. So I don't like to touch my samples any more than I have to, so I like to use these stub tweezers. They can just grasp the machined ring on the side of the SEM stubs, I don't know if that's showing up. It looks like it's kind of blurry, but these just grab onto the side like that, and then I can pull the sample out, and that way I don't have to worry about poking the top of my sample with anything. And then that just drops right into place. In theory, it appears that the set screw is slightly tight. This is why you don't want to lock the holder down, because I need to go in and loosen that screw a little bit. There we go. So that drops into place, and then I'm going to tighten the screw. When you tighten the screws, just turn until you feel a little bit of resistance. With wrenches like this, you can easily strip out these small screws, and that could potentially damage the entire stage adapter, and that would be a really big problem for us to fix. These adapters are fairly expensive to buy or make, and we really don't want to have to fix those. So there's one sample. Let me spin this around and I'll put in my other sample, the light bulb filament. And we'll just drop that in right here. And then I'll tighten that screw as well. One thing that I just pointed out, since it doesn't always happen, but let me move this camera in so I can show you. If you see here, one of the set screws is, that one on the left there is out a long way. If you ever see this kind of thing happening, this is, let me point out what I'm talking about here. This screw right here is hanging out a lot. What can happen is, as you move the stage around, there's a little bit of vibration, and it tends to work these screws out, especially if they're not locked on a sample. And eventually those will fall out, and they'll fall down into like the mechanism down here in the stage, or they'll fall into the chamber down on the floor of the microscope. So if you ever see a screw like that where it's backed out a long ways, you can save us some potential trouble by just take the wrench and just turn that in a couple turns so that it's not close to falling out. That's a really good idea. I usually try to look in the microscope periodically, and probably once a month I'll find a screw or something down there on the floor of this system. Get back in there. Okay, so now that we have our samples on the stage, the next thing we need to do is determine the height of this adapter. Again, this is adjustable. I can make it taller or shorter, depending on the sample height that goes on top of it. The way that we determine the appropriate height is we're going to put this height gauge, some people call this the elephant because it kind of looks like an elephant. We're going to put this height gauge onto the flat part of the stage, and we're going to look at where is the tallest feature on the sample in relation to this nose. Now, there's actually 3 main reference areas on this gauge, and I don't know if I can get the camera to focus on this. There we go. So come on, silly webcams. All right, anyway, the bottom surface of this nose, so right here, has a line that says 5 on it. If your sample is exactly at this height, so if we put this on the stage and we look at where the sample top is relative to that, if our sample's right there, it means we're going to be 5 millimeters away from the bottom of the SEM lens when we close the door. Now, 5 millimeters is where we want to end up for our default imaging condition. However, we don't need to load our samples right here because we have a vertical travel on our stage. We can always raise the stage up higher. So the key here is that make sure your samples are below the 5 line, so down here somewhere. And that way you can safely close the door, and then we'll bring the samples up to 5 millimeters after we turn on the microscope and start imaging. So always make sure your samples are shorter than this 5 line. Now, there's another reference surface at the top of this gauge. So this top surface up here has a 1 pointing to it. So if your samples are level with the top of this gauge, when you close the door, you'll end up 1 millimeter away from the SEM lens. I don't want to see anyone in this lab ever loading samples like that. I don't want you to be that close to the lens when you close the door. Just it's much safer to just load your sample at a long working distance and then use the stage to bring the sample closer. And if you're more than a millimeter above the top of this gauge when you close the door, you risk crashing into the SEM lens, and that's about a $35,000 mistake. So always check with this gauge. Make sure your samples are below the 5 line. Now, how far below the 5 line is kind of up to you. I usually aim for maybe 3 or 4 millimeters below it, but it doesn't really matter as long as you don't get down to this lower edge. So this lower edge right here represents the shortest sample that you can put into the chamber and still have enough travel on the stage z-axis to bring it up to 5 millimeters. So as long as your samples are within this entire range right here, you should be okay to go. And again, don't try to be right at 5. It's not worth the effort. Just be shorter than that. So let me drop this camera down just a little bit so we're kind of more level with the stage. And I'm going to set my height gauge next to the samples, and I see that my samples are taller than the nose, that 5 line, so I need to make these samples shorter. So to do that, I'm just going to turn this clockwise, maybe 4 or 5 turns. All right, and let's check it again. And I'm like right at the line now, right at that 5 line with my sample. So I'm going to go a little bit shorter. Again, it's better to be short on this microscope than to be right at that line. And I ran into the locking nut, so I had to loosen that a few turns. So just keep going down a few more turns. Let's try it again. Okay, so now now you can see I'm a couple millimeters below the nose. This easily clears, and remember to check both samples, not just one. All right, you got to check every sample, especially the tallest sample. So I'm good on that sample. I'm good on this sample. So now I know my samples are at the appropriate height, and I can go ahead and secure the locking cone nut. So to do that, I'm just going to hold on to the top part of the adapter to keep it from spinning, and I'm going to turn the cone nut just until I feel some resistance. Especially on the Nova, it's a good idea that once you feel like this is tight, is just take your hand and just kind of shake the top a little bit. Make sure it's actually secure. Especially with newer users, they tend to not tighten this adequately, and then later on in your microscope session, this will come loose and it'll start vibrating, and you'll have really terrible imaging. So make sure it's secure enough. Now that being said, if you should only really have to pinch this with 2 fingers and then turn it. If you really over tighten it, you'll actually start to spin the rotation plate on the stage, and that's a good indication that you're applying too much force to it. So everything should just be nice and snug, but not over tight. And when we used to do training in person, this was much easier. I just would have everyone try it and get a feel for it, but obviously you can't do that remotely. But if you're not sure that it's correct, come ask for help. We'll check it out and just make sure that this is good. So now everything should be ready to go to close the door. For the Nova, especially because the chamber is so open, I like to always take a moment here for training and just kind of point out what you'll see inside the microscope. And I think I can do that pretty well with this webcam, actually. So if I kind of bring this webcam over here and we take a look. So this is the inside of the microscope chamber. And the main components that you're going to see inside the chamber are the objective. I can't do that. Right. So this is the objective lens, or one of 2 objective lenses for the SEM. Over here is the objective lens for the fib column. Right here on the front is the OmniProbe needle. And in the back is the 2 electron detectors. So this this thing back here, I can't point at it without getting my hand in the way, I guess. I'm not going to reach in with anything, any kind of tool or anything to point because I don't want to risk hitting the lens. But this thing back here with this like kind of wire grid on it is the Everhart-Thornley detector. That is the main secondary electron detector that we're going to use with the low resolution lens condition on this system. And directly above the Everhart-Thornley detector, right about there, there's this little tube that kind of goes into the back of the SEM lens. On the end of that tube is this second detector called the through lens detector, or TLD. And we can use either one of those detectors when working with the SEM or when working with the FIB. And I'll show that as we turn on the microscope and go through that. In the back there, the thing with the glowing lights on it is the CCD chamber camera. Now the lights show up on this webcam, but in person there you actually can't see the lights. They're like infrared or something. They only show up on the webcam. But that's the camera display that shows you what's going on inside the chamber. And if you can see, everything else in here is just kind of empty space. There's really not much in here. There's some old feed-throughs back there that we don't use anymore. The vacuum system is down in the base of the microscope. So there's a mesh screen over it, and there's a turbo pump down there. If for some reason a sample happens to fall down into here, just go ahead and reach in with clean gloves, and you can just reach in down there and grab a sample if it happens to go down there. There's nothing down there to hurt. Same thing if something falls on the floor of the microscope. It's not going to cause any problems. Just go in and grab it. Just make sure you have clean gloves on. The number one safety consideration we have on the microscope is the bottom edge of the electron lens. So this surface right here. All of the electric or all of the magnetic fields of that lens are concentrated right on that sharp corner of that cone. And if you bump a sample into that, or especially if you dent it, and make it not circular, it will destroy the resolution of this lens. So we have to be extremely careful that nothing ever runs into that surface. Now the microscope does have a touch alarm system, so if you have a conductive sample and it makes contact with the lens, it's supposed to stop the stage from moving. But if you have an insulating sample, that will not function. Also, you can still cause damage even with the touch alarm, so we don't ever want to rely on that. So we're gonna have to just be careful when we're moving samples around to not run into that surface. Some of the other stuff that's in here, actually with the webcam, I can probably show it better than in person, is back here. This is the gas injector needle. So that needle is used to deliver the carbon gas onto the sample, and then kind of up on the back, up on the top of the microscope, you can hopefully see the other gas injector. And then the part with the tube on it, which is, let me get my finger in there. Where's my finger? This thing right here is the EDS detector. So that is the, that hole there is what collects the X-rays from the sample and measures the spectra. You kind of get another view here of the Everhart-Thornley detector and the through lens detector system there. All right, so as we close the microscope, we want to go and look at the view from the CCD camera, which is going to help us understand whether or not we're going to run into the bottom of that lens. So I think we're done with this webcam view for a second. And let's all right, so here's the view from the CCD camera. You see it kind of looks at an angle across the chamber. So there's my hand in the background. So I'm going to carefully push the door closed. And as I close the door, you can see the samples appear in the image from the right-hand side. And at this point, just pause and take a look and make sure that you're not going to hit the lens as you continue to close the door. Now, if you use the height gauge correctly, you should be at least 5 millimeters away from the lens, but it's always nice to double check here as you go. So I can tell very clearly my samples are not going to hit the lens as I shut the door. So I keep pushing the door closed all the way till it stops. And now I'm going to click the pump button on the microscope software, and that will start the pumping process. So as the chamber is pumping down, it's a good idea to just give a gentle push on the door just to make sure that it seals up. If you're not sure, just kind of pull on the handle, make sure it doesn't open. Another thing you can look at is there's a mechanism up here on the OmniProbe. This component right here will be all the way out when the chamber is vented. And as it pumps down, this will get drawn down onto that screw. So if you see that component moving, it tells you that the chamber is sealed up and that it's pulling vacuum. So that's about the only visual indicator that you're actually pumping the system down, apart from just pulling on the door. If you're going to push on the door, if for some reason it's not sealing up, go ahead and push on this flat surface right here as hard as you want, or on the handle, but don't push on the stage motors feed through. If you push on this, you can damage this assembly, because this is directly connected to the inside of the stage and that kind of thing. So again, the door, you can push on it as hard as you want. You're not going to push the microscope over or anything like that. But make sure the door seals up. Otherwise, the pump will time out after a minute or so, and then your system will just sit at air pressure. But it is pumping now. It'll take a couple minutes to reach high vacuum. So while we're waiting, this I think is a great opportunity. If any of you have any questions about what I've shown you so far, please go ahead and ask, and I will answer them. Otherwise, we're just going to be waiting for a minute or two for the system to pump.
I have a question.
Yes, go ahead.
So you mentioned a little bit about, kind of sample preparation. Is that something that you will go over today, kind of the specifics of what we need to do to prepare our samples?
Not for right now, but after I'm all done going through the operation of the microscope, I'd be happy to talk about preparation for your type of sample.
Okay, yeah, sounds good.
Yep. So the system is almost pumped down, and what I can see here is, let me get this kind of out of the way. So down in the lower right-hand corner, the chamber is still orange, but I can, in the room, maybe you can hear it on the microphone, but I can hear the turbo pump is spinning up, which just from my familiarity with this system, I know we're getting close. At some point here, you're going to see the chamber pressure start to actually read a vacuum level. And then normally within 10 or 20 seconds after you get the vacuum reading, this icon will turn bright green, which tells you that you can go ahead and start imaging. There is a valve that opens when the vacuum gauge turns on. It sometimes is rather loud, so if you're in here and feeling kind of sleepy and just kind of spacing out, it can startle you. At least for me, it sometimes gets me. But once you hear that pop noise, that's a good indicator that, there it goes, that you can expect the chamber to be pumped down rather quickly after that. All right, so there you go. You see we have a vacuum reading, and this icon turned green, which tells me that the system is high enough vacuum to operate the SEM. Now to turn on the SEM, we are going to go to the beam control tab, and we're looking for this beam on button right here next to column. And what I see right now is that a lot of these functions are disabled. And the reason for that is these functions in the panel and in the toolbar and in this hand panel that I've set up the webcam to look at, they all apply to the active selected quadrant. So we have these 4 quadrants on the screen, and if you click on one of them, you'll see it gets a blue data bar, and that is the active quadrant. So if I single click on quad 2, that makes this the active quadrant, and now all of these functions would apply to this microscope column. So that we can control either the SEM or the FIB with the same set of controls just by picking the appropriate quadrant on the software. Now the way to tell what quadrants go to which microscopes are to look at the little icon in the bottom left corner. The FIB icon is this little yellow and blue atomic nucleus symbol. So that's focused ion beam. The CCD camera is the light bulb, and the SEM is the electron cloud symbol. You can change the quadrant mapping by picking the quadrant and then going up here to the top left corner of the UI, and you can select different source signals. For example, if I pick the light bulb for quadrant 2 and then hit the pause button in the toolbar, I can now have 2 identical CCD camera images. Now, there's really no point in doing that, but I just want to demonstrate that you can change these around. On the other FEI tools in our lab, there are many more detectors available, and it's much more common, especially on the Helios 650, to reassign quadrants to multiple quadrants for the SEM, especially if you're doing a secondary electron and backscatter imaging at the same time. What we would normally do is have like quadrant 1 be your secondary electron image, and quadrant 2 could be a backscatter image. Or you can have multiple signals from the backscatter detector, and you can show those in like all 4 quadrants if you want. On the Nova, because we only have the 2 detectors, normally we would have quadrant 1 as the SEM and quadrant 2 as the FIB. So let me set that back up. This is kind of the default condition. And then quadrant 4 on all of the FEI tools is the default for the CCD camera. Again, it doesn't need to be. You can change it around if you see fit, but I would expect you will find the system in this kind of configuration when you come to use it. So if we want to turn on the SEM, we need to take the mouse and click on quadrant 1. And now all of these controls in the panel apply to the SEM. And the beam on button is available. I can go ahead and click on this once. And now we'll open the column isolation valve, which you'll hear it. It'll be like a pneumatic click. You'll hear it in the room. And the button will turn yellow. This is, I think, an important point, is make sure the button is yellow. Unfortunately, the text in this always says beam on, and this is a question I get from new users a lot, is that they will accidentally double click this button, and they think that the SEM is on, and then they can't figure out why they don't have an image on the screen, because you can actually start scanning and you'll just get a black screen that shows nothing. And it's because they either forgot to hit the button or they hit it twice accidentally. So make sure the button is yellow. Yellow means that it is actually energized. Now, once the beam is on, you have to start the scanning. It won't start automatically. So to start and stop scanning on a quadrant, you select the quad and go up in the toolbar and hit the pause button. Or if you really like keyboard shortcuts, if you go to the scan dropdown, there is a start, where is it? I don't use this very much. I always forget where this shortcut is. But there's a start and stop scanning function key. Why can't I see it? Anyway, oh, F6, right. It's right at the top. I don't know why I'm not seeing things today very well. So if you hit F6 on the keyboard, that does the same thing as clicking the pause button in the toolbar. There are a lot of keyboard shortcuts on this microscope. I'll mention a couple if I use them, but feel free to, you can just kind of look around in these drop downs, and the software does a pretty good job of showing you the equivalent shortcuts for these functions. You can also go to the help menu and choose documentation, and this will bring up the FEI user guide for the Nova. This is a PDF, so we have copies of this on the FOM server, also on the email server. If you want, you can save a copy of this for yourself. But inside here, and I always forget where it is, but there is there's a page or two where it lists all of the shortcut keys. I think it's under basic operations. Anyway, it's in here, I promise. The other microscopes actually have the keyboard shortcuts as a separate PDF document, so you don't have to go search in there for it. But feel free to take a look at that user guide. I think it's a helpful reference. Unfortunately, the user guide doesn't do a great job of telling you how to use the microscope. It basically defines what all of the functions do, and tells you like how to interact with the microscope, but it doesn't really give you the step-by-step procedure for your experiment. But I guess you can't really fault FEI for that. They wouldn't know how to write it for every single application that we want to do. All right, so getting back, I'm getting off track. So we have the beam on. We're going to go up here and hit the pause button, and now we have some kind of a live image. Now, hopefully you see something when you start scanning, but you may or may not. You may find that if the last user left the brightness and contrast very, very messed up, you may have a black screen. If you start out in the center of this stage adapter, for example, if you start out like this, you're going to have a black screen no matter what you do. So what I would suggest is the first thing to try is to lower the magnification. This big knob in the center of the hand panel is magnification, and just turn this counterclockwise until the magnification stops changing. And this will give you a view of something, at least hopefully. So at the lowest magnification, you should see a large circular feature on the screen. This feature is the inside of the electron lens. And you should always see that, even if you don't have a sample underneath the chamber. So you see as I move around here, no matter what, even if there's no sample beneath the lens, I can always see that feature. So if you're at the lowest magnification and you can't see this, the next thing I would try is to adjust the contrast and the brightness of the image. And you can do that with the contrast and brightness knobs. Or you can use the auto function up in the toolbar. So this button right here, auto contrast brightness, if you click on this, it will, the software will do its best to adjust brightness and contrast for you. Or again, you can do it manually if you want. If you don't like turning knobs by your fingers, there's also mouse commands for most of these functions. So over here in the beam control, down at the bottom, you have a slider for contrast and brightness. This does exactly the same thing as turning the knobs. So if you want to operate by mouse control instead of the knob, go ahead. And you can actually see the numbers here will change when I spin the knobs. So it's the same exact function. The other controls on the hand panel are there's an X and a Y stigmator for changing astigmatism. There's an X and a Y beam shift. That's used mainly for high resolution imaging if you need to move your image area slightly. And then there's a coarse and a fine focus knob. And again, a lot of these are duplicated over here. You have your X and Y stigmator, beam shift, contrast brightness, and so on. So we have an image now, and the next thing we need to do is to move the stage and find one of our samples. Now it's very important at this point that you only move in the X and Y direction. We don't want to move the sample towards the lens. We don't want to rotate. We don't want to tilt because we haven't really established if it's safe to do so. We need to find a sample and we need to figure out how far away is that sample from the bottom of the lens. Now there's a couple ways to move on this system that I'll go through quickly. Let me just find something that we can actually look at here. The first way is to take the mouse and then double click on a feature. So if I just double click right here, that spot moves to the center of the screen. So I'm double left clicking the mouse. So as long as you can see something on the screen, you can just double click on it and you can work your way around the stage that way. The second way to move is to press down on the center wheel on the mouse. So click the wheel down and hold it. And while you're doing that, the mouse acts like a joystick. So if I move the mouse in some direction, the stage starts to move in that direction. And you can control the speed by changing how far away that yellow arrow is from where you clicked. So if the arrow is very close to the dot, it goes very slow. If the arrow is a long way away from the dot, it moves very fast. This is the fastest way to move around the stage. So you can move easily from one side of the chamber to the other using this joystick mode. This speed changes with magnification. So if you want to move the fastest possible, you want to be at low mag. If you zoom into higher magnification, it will move much slower and more controlled. Other ways to move is you can take the mouse and you can click and drag a box around a feature. And when you let go of the mouse, the stage will zoom into the center of the box. So this will change both your stage position and your magnification at the same time. So if I want to zoom in on this little black spot up here in the corner, I can draw a box around it, let go, and then the stage zooms in to that spot. If you click and drag and you don't want the stage to move, the easiest way to get rid of this function is just shrink the box down until it turns red, and then when you let go of the mouse, the stage won't move. You can also hit the escape key on the keyboard, which will delete that selection. That's a good thing to keep in mind if you're going to use the fib, because you can get into situations where you think you're drawing a pattern. For example, if I go over here and I say I'm trying to draw a pattern, I click and drag and I want that rectangle to show up on the screen. But if I'm accidentally in the mouse mode and I click and drag, I don't want the stage to move necessarily. So if you see the little magnifying icon show up, just shrink it down and then it won't move. So that function only operates if the mouse is a mouse pointer. If you have the pattern control selected, the mouse will be a little crosshair, which means that you're trying to draw shapes on the screen, which would be for patterning. Same way if you're in the image processing tab and you have a measurement selected, the mouse will be the little measurements crosshair, which means when you click and drag, you'll be adding some kind of measurement overlay to the screen instead of moving. But if you turn those off and you get back to the mouse pointer, then you get the click and zoom function. Other ways to move around are you can use the keyboard on arrow keys. So if I push, for instance, the down arrow key, the stage will move by about one field of view in that direction. Or I can push the right arrow key and so on. This movement changes with magnification. So if I go to higher magnification and push an arrow key, it still moves by about one field of view at a time in each direction as you go around. The arrow keys don't respond very well if you just hold them down. It works much better to just push the arrow key, let it move, push the arrow key, let it move. If you push them a whole bunch of times, the stage kind of moves in a rather jerky, chaotic fashion. So just kind of keep that in mind. Other ways to move around on the stage is you can go to the second tab up here in the panel called the navigation tab. And this allows you to type in direct coordinates in the 5 axes. So if you know where you want to go, you can just type in those numbers. So a good starting point, especially if you're way off in the corner, is to go to 0x and 0y. And that will take you to the center of the stage adapter, which if you have a sample sitting in that spot, then you'll be right on top of your sample. So you see we're approximately in the middle there. Or if you know where you want to go, you can type in those coordinates. You can also change this from actual to relative, and you can do relative stage moves. So for example, if I want to move, say 3 millimeters in X, I can do a delta X of 3, and I can hit enter on the keyboard, and that moves me 3 millimeters to the right. If I want to go back left, I can do a -3 motion, and that will move me 3 millimeters to the left, back to where I was. So what I want to do is move around and go find one of my samples. It's a good idea to pay attention when you load your samples to know where the relative positions are of those stubs. Otherwise, you have to just sort of randomly move around and try to find things. On this holder, because it has the 4 arms, what I would recommend you do is just drive out along one of the arms. And if you run into an empty hole, then you know that you're on one of the, the empty spots. So then go back to the center and then go out in another direction. They're all 90 degrees apart. So if I go out here and then I go to the right, we'll follow one of these arms out. And okay, here, this is one of my SEM stubs. And I get out here and I say, okay, here's one of my samples. And then once I see it, I can use the double click to move that to center. Now, if I want to come back to this spot later, maybe I don't want to start with this sample, I can go over here to the navigation control and I can click add, and that saves this location as position 1. And if I want to rename it, I can click on it twice slowly and I can type in a new name. So let's call this spark plug. So now I've saved this stage location. The saved positions save all 5 coordinates. So just keep that in mind. When we come back to this, it will go back to this same set of 5 coordinates. So let's go find my other sample, which I remember that it was opposite of this one. So if I drive to the left, there's the center hole in the stage adapter, and I keep going. And okay, here's the light bulb filament sample. And I went too far. Let's double click and we'll come back and find this. Okay. So once you locate the sample that you want to start on, the next process is to measure the distance between the lens and that sample. So once we want to know what this gap is. To do this measurement, we're going to focus the SEM on the surface of the sample. Now I'm going to make this full screen so it's easier to see. This keyboard shortcut for this is F5, or if you don't want to remember that, you can go to the window drop down and you can choose single versus quad image mode, and you can see it tells you it's F5. So if I hit F5, it makes that full screen. And I'm going to increase my magnification just a little bit so I can see this a little better. And also my brightness and contrast need to go up a little bit. And let me scoot this out of the way slightly. Now, in my data bar down here at the bottom of the screen, one of the parameters that's visible is working distance, WD. And it says it's 5.0 millimeters. That tells me the distance the microscope is focusing to right now. Now, the image on the screen is not in focus because the sample is not 5 millimeters away from the lens. So what I'm going to do is I'm going to turn my focus knobs and try to get that image to become sharp. And once it's sharply in focus, then this parameter down here is a good measurement of the distance between the lens and the sample. Now, the one thing you have to be careful of is don't do this focusing operation at really, really low magnification. It's very easy to mess up the measurement. I recommend that you get your magnification at least to 2000x. So right now I'm only at about 190x, so I'm fairly low magnification. I'm going to increase my magnification to about 2000, and now I can tell that I'm still very out of focus. So then I will continue to adjust my focus using either the fine knob or the coarse knob. It doesn't really matter which one you use. One just goes faster than the other. And I want to try to get the image of the sample to look sharp. Now, if you have a very small feature, say you have nanoparticles on a wafer or something like that, 2000x might not be good enough. So you need to make sure your magnification is suitable that you can actually see something to focus on. You don't want to be just trying to see like a big gray image. So right now I can kind of see the edge of this this tungsten filament. But if I move around a little bit, you know, maybe and zoom in a little bit, I can find some more obvious features. Like here's some little particles on the surface. And let me just make sure that those are actually in focus. So 2000x is my recommended minimum magnification for doing this, but feel free to go higher if your sample requires it. You want to make sure you can see something. So now that I know I'm in focus, I can look at the parameter down here, and it says I'm 8.9 millimeter working distance. So that means that is the measurement between the bottom of the lens and the top of the sample is 8.9 millimeters. Now, the microscope software doesn't know that. The microscope software over here for the z-axis still shows 0 millimeters, and it shows that the positive direction is up. And in order to get these values to link, we need to go to the toolbar with the SEM image selected, and we're going to push this icon up here that's called Link Z to FWD, and it says it's not linked right now. When I push this icon with the little red question mark on it, it will transfer that working distance value, whatever it happens to be, to the Z coordinate. The other thing that'll happen is the positive direction for Z will change. Positive will now become the down direction instead of up. So let's do that and we'll see what happens. So I'm going to go up here, I'm going to click the link button, and it changes from a red question mark to an up and down green arrow, and it says already linked, and now you can see that that 8.6 or 8.85 millimeter working distance is now reflected as the z-axis, and the positive direction is now showing as down. So when you start out and you have not linked the working distance to Z, 0 millimeters is the lowest height that the stage can go to. 0 is down. After you link, 0 millimeters for Z will put the sample right against the bottom of the SEM lens, which most of the time will cause a collision. So keep in mind which way you want to move the stage. So now that we're linked, positive numbers move me away from the lens, smaller numbers move me towards the lens. The linked coordinate system is much more useful for us as a microscopist because we don't really care about the height of the stage. It doesn't mean anything to us. What we care about is how far away we are from the lens. Now, for some of you, you're going to be using other instruments in the lab, especially the test scan SEMs. Those have a slightly different method for doing this, but it still involves focusing on the sample to determine the distance between the lens and the top of the sample. But just keep that in mind that you can't necessarily use the same techniques on every microscope. They're all slightly different. Once we're linked, we can then type in whatever working distance in the Z coordinate that we want to go to. 5 millimeters is going to be the standard SEM condition. So I'm going to type in 5 for Z, and I can either hit enter on the keyboard or I can hit this go to button, and that will move the stage. Now, while the stage is moving, the go to button will show stop. So if I click on the stop button, it will freeze the stage wherever it happens to be. I can also push the escape key on the keyboard, which will stop the stage as well. So if you think you made a mistake and you're worried that you're going to crash into something, hit the escape key on the keyboard or click this stop button, and that will freeze everything. So we're going to hit go to, and that's going to bring the sample up to 5 millimeter working distance away from the lens. Now this is an approximate 5 millimeters. As you go closer and closer to the lens, you can improve the accuracy of that distance measurement. And the software will kind of tell you to do this by changing this icon up here to a red circle. So if it goes from a green arrow to a red circle, the software is telling you that you should focus a second time and click on this link a second time, and that will update the value more accurately. So let me adjust my focus again, get a little bit better focus. And this is actually pretty close, but you can see that my working distance shows 4.9 millimeters instead of exactly 5. So I just go up here, I click my link button again, and now this number in the z-axis should be more correct. So if I want to be exactly at 5, I would then type in 5 a second time, and now we should be much closer to exactly 5 millimeters. So anytime you see that icon up here, change the red circle, just check your focus and update that link value so that way you know you're exactly where you want to be. So let's go ahead and save this position. I'll click Add, and we'll call this filament. And let's see what happens if I go back to the other sample. One of the, I consider it a little bit of a downside to the FEI software, but the FEI software does not remember the link between different samples. So because I linked my working distance on the light bulb filament, if I go back to the spark plug sample by double clicking on it, the stage will go back to the position that it was in when I saved it, but the focus of the SEM won't be correct because the SEM thinks my link value is related to this other sample. So it thinks my working distance is at 8.7 millimeters because that's how far away the filament sample is from the lens right now. But because the spark plug is probably a slightly different height, that link value is no longer correct. So what I need to do is when I go to a new sample is I need to make sure my focus is correct, and I need to update my link every time. So I get back in focus, I can update my link, and now my z-axis correctly reflects the distance to this sample from the lens. And now I can bring this one up to 5 millimeters as well. And just like before, I want to do this process twice. So I focus, link, go to 5, focus a second time, update my link, and then make sure I'm right at 5 millimeters. Now I want to update my saved position, so I'm going to click on spark plug once, and I'll click update and say yes. So now I have saved positions. Both of these samples are exactly 5 millimeters away from the lens in these saved conditions. But again, the link is not correct, is not going to translate between the two. So if I go back to the light bulb filament, the sample is going to end up 5 millimeters from the lens, but because the link is to the spark plug sample, the focus is going to change to an incorrect value. So the focus says it's at 4.4 millimeters, which is not right. So when I get back here, I just change my focus and update my link. And you can see that we're right at 5 millimeters still. It's just that that focus value was wrong. Now, this process is important, so I want to make sure that all this is clear. So if you have any questions right now about this, please ask them, because this is actually very important for the safety of the microscope, because we don't want to accidentally drive a sample into the side of the lens and damage the lens. Okay, so we've positioned our sample. We're on top of the sample I want to start with. We're at 5 millimeter working distance. The next thing we're going to look at is setting the conditions of the electron column. The main conditions that we need to worry about are going to be the accelerating voltage of the SEM, the beam current of the SEM, the detector that you're going to use, and the detector mode, and the working distance. Now, a lot of times the detector is going to be chosen for you automatically based on limits of the microscope, or just there's going to be a best detector to use. In this case, we're starting out with the Everhard Thornley detector, and we can see the detectors by going up here to the detector tab in the panel. And we have two different detectors available, the Everhard Thornley or the TLD. You can see here that the TLD in secondary electron mode is going to be rather on the noisy side. The TLD detector is best suited for the high resolution SEM conditions, and the Everhard Thornley detector is better for the low resolution conditions. So I would recommend you start off with the ETD detector. Also, make sure you check the mode of operation. If the last user left it in backscatter mode or custom mode, you may not get a very nice signal when you start out. So secondary electron mode is going to be my recommended starting point for this. The working distance, again, the default that I would recommend you start at is 5 millimeters. As you go closer to the lens, your resolution will improve on the SEM, but you may find that you don't really need that extra resolution. And as you go closer to the lens, it makes it more dangerous and more likely you're going to bump into the lens. It also limits your ability to tilt the stage and rotate the stage safely. So I would say stay at 5 millimeters until you have a reason to go closer. I don't know of any strong reason why you'd want to go further away than 5 millimeters, because all it's going to do is drop your resolution. It's not going to make the microscope operate any better to go, say, image at 7 or 8 millimeter working distance. So I would always go to 5. So those are two of the conditions I mentioned. The other ones would be the accelerating voltage and the beam current. To change accelerating voltage, you're going to either click in one of two spots. There's a drop-down menu in the toolbar, which gives you the choice of some preset voltages. And you can simply click on these to select them. So if I want to image at 10 kV, I can select 10 kV, and now I'm imaging at 10,000 volt potential. The other spot you can go is in the beam control tab right here where it says high voltage. You can type in any number that you want with a 10 volt step size. So don't feel that you are constrained by those preset numbers. So if for some reason you want to image at 8,500 volts, that's fine. The microscope will let you go to any voltage you want. The smallest voltage you can image with on this tool is 300 volts, and the highest voltage is 30,000 volts. On every microscope, there is going to be a range of voltages that are going to give you your best possible resolution. And I would recommend you try to operate in that type of condition for each SEM. In my experience on the Nova, this tool operates best between around 3 and 8 kV accelerating voltage. With 5 kV being kind of right in the middle, it's a really good all-around voltage. If you operate much lower than 3 kV, you will see a notable drop in resolution on this tool. Now that being said, you can still image at 1 kV or 500 volts if you want. Just don't expect to be seeing the tiniest features on your sample because you'll start throwing away resolution really quick. If you image at higher voltages, say 10 or 15 or 20 kV, you will also be potentially throwing away image contrast and quality of image because your accelerating voltage, when it gets that high, the electron beam really starts to penetrate into the sample and you lose a lot of that surface topography information that is the whole reason for doing SEM in the first place. So I would strongly recommend against imaging higher than 10 kV for sure. On the Nova, there's really no benefit unless you're doing EDS and you need the beam energy to excite X-rays. Now that recommendation of voltage ranges, so 3 to 8 kV is what I would suggest. That doesn't apply to the other SEMs in the lab. Every SEM has its own optimum range. So if you're using the TestScan Mira 3, for example, I would probably say more like 5 to 15 kV would be a good range for those SEMs. If you're using one of the Helios systems, I would recommend something like 500 volts to maybe 3 kV. The Helios microscopes operate much better at lower voltage than any of the other SEMs in the lab. So just keep that in mind. Don't blindly use 20 kV because that's what you read in a paper that was published 10 years ago as your imaging conditions. You want to try to get the best image you can out of these tools. So let's just start at 5 kV. Again, that's a really good default condition. If you don't really know where to start, I would start there. And then for beam current, your beam current is only changeable by this one drop-down menu in this software, and you have seven choices. The smallest beam current will be at the top of the list. The largest is at the bottom. As you go to smaller and smaller beam currents, your resolution of the SEM will get better, but your image will get noisier. So you'll have to do slower scanning. Focusing can be more difficult and more frustrating. But if you need to look at the smallest possible features that this microscope can resolve, you're going to want to be looking at these small beam currents. So I kind of group this into 3 ranges. So the top 3 beam currents are like your ultra high resolution conditions. The middle 3 beam currents, so 98 picoamps through 1.6 nanoamps, these are like your medium resolution conditions that I would consider kind of the all-around conditions. And then the bottom 3 are the analytical conditions where you're going to want to be doing EDS analysis or if you're using the SEM to deposit material, you're going to want to be down here. The absolute numbers in this list will change a little bit based on your voltage. So for example, if I pick the middle value, the 0.4 nanoamps, if I change my voltage to 10 kV, you'll see that that middle value is now 0.54 nanoamps. So just kind of watch out for that, you still have the same seven positions, but the absolute numbers change with the accelerating voltage. But my recommendation still is the same, that kind of the middle three are good all-around conditions, and then the top three are your high-resolution conditions. So let's go back to 5 kV, and we're going to use 0.40 nanoamps. After we have chosen our accelerating voltage and our beam current, the next step is to align the microscope column. There are two main steps to doing this. You need to find a sample first. You have to have kind of a reasonable image to do this. In this case, I can see the surface of my sample. I'm reasonably in focus, so this will work. The two alignments are both found in the beam control tab. The first one we're going to do is called source tilt, which is this adjuster right here. Source tilt will change the angle of the electron beam as it comes down the column from the field emitter. If we change the angle too much, the electron beam will crash into the side of the column and you will get no image. And you can see that if I grab onto this adjuster and I just move it to one side, you see we lose our image. Now you can do this alignment by just moving this around and trying to find the brightest signal that you can. But there's a much easier way to do it on the FEI software, and that's by using this button called crossover mode. When you click on the crossover mode, let me make this full screen, you will see a bright circle somewhere on the image. And the software adds this green X, which is always to the right of center. The green X represents the center of the column optic axis. And wherever the bright spot is your current alignment point. So if I mess up my source tilt really badly here, you can see the bright spot is over here to the side. What I want to do is I want to put the center of the bright spot right on the center of the green X. Ignore the yellow crosshair. That just represents the center of the view image, and that can be turned on and off in the window. I can turn off center cross. So the green X is the center alignment point. So I'm just going to grab onto the 2D adjuster for source tilt, and I'll drag this over and position it right on the center of the X. Just like that. This alignment should only take you a few seconds. It shouldn't be difficult. One thing to watch out for is you may find that under certain conditions, like for example, a very small beam current, like let's go to 25 picoamps. If I go to crossover, well, it shows up good. You may find that you can't see the bright spot very well. In that case, what you can do is turn up the contrast of the detector, and that will show you the bright spot somewhere on the screen. You can also see that the size of the spot changes with beam current, but the alignment principle is the same. You still want to put the center of the spot on the green X. Every voltage and beam current combination has its own alignment. So every time I make a change to one of these values, you have to come back in and realign the source tilt. So just keep that in mind. You know, don't perfect your image before you check these alignments, because if you change voltage or beam current, you're going to have to redo them again. So again, go to crossover, adjust your source tilt to put that spot right on the center of the green X, and then turn off crossover, and we go back to our regular imaging mode. The next alignment is called lens alignment, which is right here next to source tilt. And lens alignment is going to shift the position of the electron beam as it passes through the objective lens. The way we find the center of the lens is by turning on the lens align button, and this will activate a modulator, either a high voltage modulator or a lens current modulator, depending on what voltage you're using. And with the modulator on, we're looking for any kind of motion in the image. And we want to change the lens alignment to get rid of that wobbling. I'm going to, let me turn off lens align for a second. Let me zoom in on one of these more obvious particles. And let me make this a little sharper with focus and astigmatism. All right, so if I turn on the lens alignment, And let me really mess this up so this is really obvious. Okay, so my lens alignment is really bad right now. And with the lens align button turned on, you can see that in addition to going in and out of focus, those features on the surface appear to be shifting, right? They're shifting kind of back and forth along this direction. So I want to move my lens alignment to the adjuster to get rid of that motion. And you can grab onto this adjuster and drag it up and down and left and right. You can also grab onto this green crosshair thing that shows up in the center. It does the same thing. It's just kind of two ways to do this. I recommend that you grab onto either the horizontal or the vertical line segment, kind of off to one side, and that limits you to only adjusting one direction at a time. So if I grab onto the horizontal line and I drag it up and down, I can either fix or make worse the vertical wobbling. So what I want to do is try to get this image so it's only shaking left and right. So something like that is good. Then I'm going to grab the vertical line segment and I'm going to move it to the left or to the right. And I'm going to try to get rid of the last little bit of the wobbling in the horizontal direction. And I went too far there. This process, I think, is one of the skills that takes the most practice if you're not used to operating SEMs. Just to do this efficiently, you'll just have to practice at it. If you find it's taking you more than a couple minutes to get this fixed, come ask for help. We'll be happy to help you do this. Now, I fixed the horizontal alignment. It looks like I've got a little bit of vertical shaking again. So let me try the vertical alignment one more time. And that looks pretty good to me. How perfect you get this alignment is going to be up to you. The better the alignment, the better the resolution of your image, but there's a trade-off there. We don't want to spend 20 minutes trying to fix the column alignment because you could get the same improvement in resolution just by going to a smaller beam current. So don't stress out about this. The main point is we don't want to have the image, noticeably shaking all over the screen with the lens align button on. The other consideration is do the lens alignment at a similar magnification to where you're going to take your images. You don't want to do the lens alignment down at 250x if you're going to be taking images at 100,000x. It won't do you any good. So make sure that you turn up your magnification appropriately. Otherwise, you'll get very inconsistent results. All right, so once we have our lens alignment fixed, the last thing to do to get a final image would be to adjust our focus and astigmatism. I'm going to go back and do focus by turning either the fine or the coarse focus knob. Now, one thing that helps with focus is to change your scanning speeds, which can be done with this adjuster up here on the toolbar. The left arrow makes it scan one speed slower. The right arrow makes it scan one speed faster, or you can click the drop down and go to any scan speed in the list. Usually faster scanning makes it easier to see the image go in and out of focus. If your scan speed is really slow, like for instance like this, adjusting focus can be kind of painful because you have to wait for the whole image to refresh in order to see your improvement. The other thing you can do is if this image is very noisy at fast scan speeds, is you can use a function called reduced area. So by putting a reduced area box on top of an obvious feature, you can then change your scan speed, slow it down a little bit, and this will allow you to see enough detail to quickly adjust your focus and astigmatism. So I'm going to start with focus, and the best focus is going to be where the objects are either have very sharp edges, or if you have astigmatism, the best focus is going to be where the edges of the object are evenly blurry. And what do I mean by that? Well, let me mess up my astigmatism really badly here. Okay, so I just turned my stigmator knobs. My astigmatism is going to be terrible now. So if I go back and forth in focus, what we'll see is, let me see if I can find a little bit better spot that'll show this more clearly. Little round objects are really the easiest thing to do this on. Yeah, this looks good. Okay, so as I go back and forth in focus, on one side of focus, you should see that like all of the blurry edges are aligned in this direction. And as I go through focus, that blurriness will flip 90 degrees, and now it is all aligned in this direction. So the focal point is that kind of halfway position between those two extremes where everything is blurry in sort of a symmetrical, uniform way. So what I like to do is kind of wobble the focus knob back and forth a few times and try to get an idea of where that center transition point occurs. And everything's symmetrical, so if I make it kind of distorted one way, make it evenly distorted the other way, I can kind of use my muscle memory in my finger combined with what I see on the screen to kind of get to that halfway point, which I would say is right about here. Once you think you're in focus, then we're going to fix the astigmatism using the stigmator knobs. And it doesn't matter which stigmator knob you start with, but just pick one. I'm going to start with the first one, which is X. And I'm just going to turn the stigmator knob one way, and hopefully the image gets better. In this case, it got worse. So then I'm going to go the other way. And the image gets better, 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 better. Then it gets worse again, and then go back. So kind of wobble that stigmator knob back and forth a few times. Find the sharpest image you can only with that one stigmator, and then do the same thing with the other stigmator. So try not to be in the habit of changing both stigmators at the same time. You'll end up going in circles. So stigmator 1, the X stigmator, I do that first. Then I'm going to do the Y stigmator, same thing. Wobble it back and forth. Get my image as sharp as I can. And then I'm done with that stigmator. If you're still unhappy with your image, then repeat this whole cycle. So do focus, and then stigmator X, stigmator Y. Focus, stigmator X, stigmator Y. Just keep doing this, and each time, hopefully, you get to a better and better image. So I do my focus, that looks sharper. Then I'll go back and I'll check my stigmator X, stigmator Y. And as your image quality improves, feel free to look around, find some smaller features that might be easier to get a nice image on. Also, you can change your scanning speeds as you go, but the idea is that you should be getting better and better and better quality images as you go here. So focus, stigmator, stigmator, and that looks pretty good to me. So now our image should be as good as it's going to get with our current conditions, right? So again, we have our choice of accelerating voltage, our beam current, and our working distance. We have optimized the SEM for that set of parameters. Now we're ready to actually take a image. Okay, so to get an image, what we want to do is one of three things. We can simply slow down the scan speed by going up here and clicking the left arrow a few times. So maybe try like your 5 microsecond dwell time, something like that. And if I think, let's just say I think that image looks reasonably good. In order to save that, I need to hit the pause button to freeze the scanning, because this is still live scanning. So if I make changes to the image, it's still being updated. So I hit pause once, and the scan will finish one frame and then stop. So now I have a frozen image on the screen, and I can go to File and click Save or Save As, and I can save this image into a folder. In this case, I'm going to save it to the Nova temporary user data path, which is located on the support computer. I'll go to my folder. I'll make a new folder. We'll call it Training. Spelled there. A little bit of a typo there. And then I can save it directly. I can put in a file name. Let's just call this filament. And I can choose different types of image formats to use. And I can also choose to save the data bar or save any overlay graphics on that image. I like to use the 16-bit grayscale. That's the best quality image that you can record on the Nova. So I strongly recommend you use that one. And we click Save. So that's the first way to acquire an image. Just change your scan speed so you're happy with it. Hit the pause button. Once the scan stops, you can save it. The second way to do this is by using this button right here called Snapshot. The snapshot will cause a picture to be acquired using one of two preset scan speeds. Now, I don't really know what it's going to do. Let's just hit it and we'll see what happens. So my live speed is 300 nanoseconds. I hit snapshot and it goes to, I don't know if you saw that, it went to 1.5 microseconds. And also you see the image resolution is changing because I'm live scanning with 1024 pixels by 884. And when the snapshot's running, it's dropping down to 512 by 442. After the snapshot's done, I can choose to go file and I can click save, and that saves that image as well. The third way to get an image is called the photo preset. And the photo preset unfortunately doesn't have a button in the toolbar. It's activated with F2 on the keyboard. Or you can go to the scan drop-down menu and choose photo. And you see it says here F2. The photo preset is your slow scan preset. So if I push F2 on the keyboard, in this case, it is doing a 3 microsecond dwell time, and you can see it actually increased the image resolution to 2048 pixels. You're going to find that the previous users change these settings all the time. So it's a good habit to get into is to check those scan conditions when you start. Set them up to whatever you prefer, so that way you can efficiently use the tool. Now, the photo preset has been configured right now to open up the file save window after it's done, which is why this window popped up automatically. I'm just going to hit cancel. I don't feel like saving that again. Where you go to change all these parameters is the scan drop-down menu, and you go to preferences. And the scan preferences window will open up like this. And what you'll see is a list of dwell times. These are the dwell times available to you for live scanning. So this will match this drop-down list right here. So we're currently sitting on 300 nanoseconds, and as we go, if I click the right arrow, it'll go down the list. The left arrow will go up the list. So those live scan speeds can be altered. So for example, there's a pretty big jump here. It goes from 10 microseconds to 100 microseconds. Maybe I want a little bit more control over my live speeds. I can't add or subtract to this list, but I can change values. So I'm going to click on one of these, like the 500 microseconds, and I'm going to go over here and I'm going to change this to be 20 and hit enter. So now I have a 20 microsecond live speed available to me. Same way as maybe I don't like this 1.5 microsecond. I'm going to change this to something else. Let's make it 1. And I can hit apply and OK. So now in my live speeds, I have 1 available and I have a 10 available and a 20 because I changed those values. You can also change in here, the 2 camera icons are your snapshot value and your photo preset values. Now make sure you don't click on the number. If I click on the 1 microsecond, that refers to the scan speed preset. You have to actually click on the camera icon. So this says snapshot or photo preset. Or you can also find them in this drop-down menu here. So right now, if I want to change my snapshot settings, I click on the snapshot camera, and then all of these values can be changed to whatever I want that button to do. So I'm going to change my resolution to 1024 by 884. Let's make the dwell time a little bit longer. Okay, and now you see I only have a couple dwell times available to me. There's some software limits in here that restrict you to the snapshot has to be a faster scan condition than the photo preset. So because the photo preset is sitting on 3 microsecond dwell time, I can't choose any longer scan speed than the 1 microsecond right now. And I'll see the opposite effect on the photo preset, that I won't be able to choose any faster scanning speeds than the 3 microsecond because the photo is sitting right here. So if I change my photo preset down to like 100 microseconds and hit apply, now when I click on my snapshot, I'll have a lot more choices available for this. You're also limited to only choosing dwell times that are available for live scanning. So if I want a different scan speed, say, for example, I want a 2 microsecond scan for my snapshot, I can't choose it here until I make one of my live scan speeds 2 microseconds. So let's make one of these 2, hit apply, and now I have a 2 microsecond speed available for snapshot. A lot of this limitations are different on the Helios tools. FEI realized that this was just a stupid software limit, and there's a lot more flexibility on those other microscopes in terms of setting up your scan speeds. But you still can access any speed you want. You just have to make sure it's one of the live speeds first, and then you can set it as a photo or a snapshot. So let's do 5 microsecond dwell time for my snapshot, 1024 by 884 pixels. We can do frame integration if we want to. That can sometimes help if you're doing really fast scanning. And then you can tell the software to record in either 8-bit or 16-bit mode. I always do 16-bit. I don't see the point in recording in 8-bit mode. It just lowers your dynamic range in your image. And then the action is what happens when it's done. So if it's set to none, it'll just pause the screen. If you set it to save, it'll auto-save the image. And if you set it to save as, it'll bring up the file save window. So let's just leave this as none, and we'll hit apply and OK. So now if I hit snapshot, I should get that 5 microsecond scan instead of the other condition that was mapped to it. And same thing with the photo preset. So scan, preferences. I can set my photo preset to whatever conditions I want. And this time, let's set it to be autosave and hit apply. So now if I hit F2 on the keyboard, that'll take that nice, relatively slow 20 microsecond scan. And because it's set to save, when it's done, it'll autosave the image. It'll always go to the last file name and last directory that you saved as. So in this case, because I saved an image as filament, it will use that as the file name. It'll add a number to the end of it so it's unique, but it'll go to that same directory as well. And there it goes, it auto-saved. And if I look at my folder now, training, you can see that filament-002 is the image that I just recorded. Now, if you want to change the directory or the file name, what you have to do is go up here to File, click Save As, and then basically save a dummy image in a new folder or with a new file name. So let's just say I want to change this to be test and click Save. So now all subsequent images from this point will start with test, and they'll be test 001, test 002, and so on. And they could go to a different folder if you set it up that way. Okay, so the next thing I want to show you, we're getting close to the end here, is I want to show you the high resolution lens mode. Right now we're using the low resolution lens on the microscope. If we go back and look at the chamber camera for a second, this conical shaped lens hanging down from the roof of the microscope is the high resolution objective lens. There's actually another lens inside this that is the low resolution lens that we're using right now. So you have two distinct objective lenses. When we switch the lens mode to the high resolution lens, we will hopefully get much better resolution than what we're getting right now. The way you switch the lens mode is this icon up here in the toolbar. It has a little drop-down menu on it, but if you just click the button, it'll switch to back and forth between high and low resolution. If you click the down arrow, you'll actually see there are 3 modes available. Mode 1 field-free mode is your low-resolution objective lens mode. Mode 2 immersion mode is the high-resolution objective lens mode. And Mode 3 EDX mode uses both lenses at the same time. Mode 3 EDX is sort of a special mode for when you're doing X-ray analysis. Otherwise, I wouldn't recommend using it. It doesn't get you really any more resolution than Mode 1, but you do need this if you're doing X-ray analysis. When I switch to Mode 2, the software is going to automatically change the detector to the through lens detector. The through lens detector is the only detector available with the high resolution lens mode. Also, because we're going to a completely different objective lens, I would expect that my image will go out of focus. I'll probably have astigmatism problems, and I'll need to go and check my lens alignment. So just keep that in mind that if you know you're going to use the high resolution lens, I wouldn't waste a lot of time aligning the column because you're going to have to redo it all again anyway. Just use the low resolution lens to find your sample, switch to high resolution, and then you should be all set to align everything. So let's go ahead and do that. So I'm going to go up here and just click this button. And instead of a single lens in the icon, it's now a double lens. So that means we're using the high resolution lens condition. And just like I told you, the detector switched automatically to the through lens detector. So now we need to dial in our conditions again. We don't technically have to redo source tilt. The source tilt on the Nova does not change between the low resolution and high resolution lens. It's always a good idea to check it just to make sure. Again, if you can't really see the spot, just turn up your contrast. And you can see here the source tilt is still the same as it was because I adjusted it in mode 1. But the lens alignment for sure will be wrong. So let's start out, let's go to full screen by hitting F5. Let's change our focus a little bit. Maybe some brightness and contrast adjustment. And let me find that area we were looking at. Same spot. And let's turn on the lens alignment, and we'll see if we have any lens alignment issues. It actually looks pretty good. It's not always the case, but you want to check it. The Microscope software actually has a memory table for these alignments. So if you use a condition that the last user or maybe a user from a previous day has already aligned, I wouldn't be shocked that the alignments are pretty good. Now, if I pick a voltage condition, like say if I go to like 1 kV, my guess is that no one's used 1 kV in a long time, and probably the lens alignment is going to be really bad for that condition. But always check it. And then we need to double check our focus and astigmatism. So let's slow down our scanning here, and we'll check focus. And also astigmatism. And I'm going to raise, my hand panel camera shifted. Check my astigmators. And that looks pretty good. Now, these objects are kind of large, so I'm not seeing a gigantic difference in the image quality, but if we look at some of these smaller features, like down here in this corner, we should hopefully see better image quality. One thing that happens on the Nova sometimes is that you may see some drift in the image. This usually goes away after a minute or so. What's happening is that when you switch on that high resolution lens, the lens starts to warm up and it can change some of the imaging alignments and things like that. So once the temperature of the lens stabilizes, I would expect this shifting to kind of go away. The Helios microscopes shouldn't have this problem. They operate with what's called a constant power lens, but this is pretty typical when you shift to high resolution mode that you may see some instabilities for a minute or two. If it keeps drifting for a long time, then come ask for help, because it's probably indicating there's something wrong with the microscope or your sample is actually moving. But hopefully this goes away here within a few seconds or a minute or so. All right, so let me see if I can get this a little bit better quality image. So I do my focus. And I can do my astigmatism. And I would say that's pretty good. Now at this point, if I want to recenter my image, I can try to move the stage, but if I double click, I'm asking a mechanical stage to move on the order of like 100 nanometers, and it just doesn't work well. This is where the X and Y image shift comes into play, that I can use the image shift to move that image location around a little bit to kind of frame my image without having to move the stage mechanically. So that allows for much more precision in terms of setting up your image location. So let's go ahead and hit photo, and we'll see what this looks like. I think it's still drifting a little bit, so I'm expecting a little bit of a shear in this image, but hopefully you get the idea. Also looks like maybe this spot got a little bit carbon contaminated. I don't know, hopefully you can see this. There's like a little bit of a film kind of growing on some of these surfaces. That is probably carbon residue that is building up as I'm scanning. You can see it right here too. So that carbon contamination is either coming from my sample or it's coming from inside the chamber. And that film will eventually build up, and it hinders the ability to look at really small objects. So maybe I need to look at cleaning my sample, which we have a plasma cleaner in the lab for doing that. Or maybe as a service action, maybe we need to look at cleaning the chamber a little bit. Most likely it's the samples that are dirty. Usually the chambers stay pretty clean as long as everyone's using gloves and using clean samples. Okay, let's go over to the other sample, my spark plug sample, because that one has a lot smaller features on it. And I think you'll see the difference between the low resolution and the high resolution lens much better over there. Okay, again, when I go to a new sample, the focus is all messed up because the working distance link is wrong. So I want to get in focus. And once I'm in focus, I can try to find some small features. And then I'm going to update my link, and we should still be right at 5 millimeters, which we are. Okay, so let me zoom in here. This sample is platinum with carbon little nanoparticles on it. And just to kind of demonstrate what types of structures should be viewable to you, let's check our column alignment again. So our crossover is still good. Let me check my lens alignment. The lens alignment looks pretty good. And then I'll use reduced area and I'll check my focus and astigmatism. This sample looks a lot more stable, so either the lens has already stabilized, or maybe that that other sample isn't super stable. It is drifting a little bit. So let me beam shift a little bit here. We'll slow down our scan speed, and I'm going to pause this for a second. Okay, so I have my display right on top of the smallest particles. Let me try that again. Okay, so here we have an image. I would say I could probably do better. This isn't fantastic, but let's just put a measurement on here. So I'm going to go up to my image processing tab, and I'm going to grab a circle measurement, and let's draw a circle around one of these particles. And okay, that one's about 16 or 17 nanometers. This one's about 14. So without trying too hard, we're looking at sub 15 nanometer features. Let's see if I can get the focus a little better here. I might also need to look for just some smaller stuff. This sample has some tinier features. I just have to go looking for them. Let me turn my center cross back on. All right, so this type of magnification, I'm at 500,000x. I'm kind of pushing the limits on this microscope right now. But hopefully you can see that I can actually tell that there's some really tiny little particles here. The image quality is not fantastic, but that's on the order of like 8 nanometers. Maybe this little guy here is about 10. Um, this is with a moderate beam current. I'm not using one of the tiny beam currents. I'm using the 0.4 nanoamps. I'm at 5 kV. I'm still at 5 millimeter working distance. And I can easily see features below 20 nanometers. And certainly I can detect that there are some features below 10 nanometers. I wouldn't say that image quality is fantastic for something that small, but just this is what I would consider pretty typical of where the Nova starts to run out of capability. So if your project is going to require you to constantly look at stuff in this type of size scale, like 10 or 15 nanometers, I would suggest that you look at the Helios or the Helios plasma fib as an alternative, just because the resolution of those systems is just a little bit better, and it'll make your life easier if you're looking at this kind of stuff. But if you're looking at features that are more on the order of like 30, 40, 50 nanometers or bigger, like some of this other stuff, I think the Nova will be very, very suitable for you. And let's see what happens. If I want to really improve my image resolution, what I would try is I would go closer to the lens, and I would probably drop down my beam current a little bit, and I would also probably drop my voltage down a little bit. So let's try that. Let's see if I can get a little bit prettier image. So I'm going to drop my voltage down to 3 kV. I'm going to drop my beam current down to 68 picoamps. And I'm going to move my stage, instead of being at 5 millimeters, let's go up to like 2 millimeter working distance. So we're starting to get closer to the lens here. Now, because of all the things I just changed, I'm going to have to realign the column because I changed the voltage or the beam current. So let's go to beam control. We'll check our crossover spot. And sure enough, that's off a little bit. So we align the crossover. And then we'll check lens alignment. When you're at really low magnification with lens alignment, you get this kind of weird distorting effect. What you want to do is just turn up your magnification a little bit, and then it'll look better. So let's fix lens alignment. That looks pretty good. And then let's check our focus. And we'll keep zooming in as we go here and just look for smaller and smaller features that I can see. And then I'll change my astigmatism. Again, focus, and then astigmatism, and then astigmatism. So you're happy with your image. And I can always go back and check my lens alignment one more time, especially if you're really trying to push resolution. You're going to want to be checking this frequently. I say that's good enough. And so let's zoom in here. We'll do my focus one more time. All right, so now let's see if that looks any better. Let me find some of these small particles. Oop, I shouldn't have done that. I tried to move the stage. I should have used beam shift. All right, so we go back up to that real high magnification. And I don't know if that looks any better. Maybe a little bit. Yeah, I would say it's to me, I think it's a little bit better. Maybe it's just not a great spot on this sample, but generally you can get more resolution as you go closer to the lens and as you lower your beam current. But I also drop my voltage, which dropping the voltage has another big effect on the image, and maybe I went too low. The best voltage for a sample is not always the same. It depends on what you're looking at. So on some samples, the best voltage might be 3 or 4 kV, and the other samples it might be more like 7 or 8 kV. It really depends on like the density and the atomic number of what you're looking at. So anyway, just to kind of give you an idea of what is reasonable here. So these are 10, 20 nanometer type features. I can see them pretty easily. Maybe a little bit fuzzy at these magnifications, but to be honest, I don't see a lot of users on the Nova really going after particles like this kind of size scale. This is like 20, 25, 15-ish, that kind of thing. You can certainly see them. Again, I would probably push you towards the Helios if this is what you're going to be doing all the time for your project. So some other neat things that you can do with this tool is let me go back up to a little bit higher beam current. And let's say you need to know if there's multiple types of materials on your sample. Right now I'm imaging with the secondary electron mode, which secondary electron mode shows you topographic contrast mainly. But let's say you want to use backscatter contrast. We can go to the detector tab and change from the TLD detector in secondary electron mode to backscatter mode. And when you do that, it will throw you out of focus. But once you get back in focus, the backscatter mode will show you where if different composition materials are sitting on your sample. So in a backscatter image, anything that's brighter should be higher atomic number, and anything that's darker should be lower atomic number. So in this case, I can tell that this kind of blobby thing here is actually made up of two different materials, platinum and carbon. Whereas in the secondary electron mode, because I only see the topographic contrast on it, it just kind of looks like, let me get back here. One, it's charging up really bad, but if you kind of look through the charge, you can see that you can see the little dots stuck in there, which from the backscatter image, I know those are platinum, but in the secondary electron image, it's not really obvious that that's a different material. So the backscatter mode of the TLD detector is really nice for doing this kind of thing. You can also use the detector modes to filter out charge. So like in this case, you see that this particle is charging up a little bit. What you want to do is change the value of this electrode called the suction tube. When you change mode, so if I go to backscatter mode, you see the suction tube goes to -50. In secondary electron mode, it goes to +50. And there's some other modes on here, but I like to just change it with the custom slider. And as you get to 0 volts and go negative, what you'll be doing is you'll throw away any electrons that are affected by that charge. So there's still a little bit of charge there, and as I keep clicking it down, you can see I kind of get rid of the charge in the image. And so I'm at -8 volts here. So in effect, what I'm doing is I'm only imaging with electrons that have higher energy than 8 eV, which are going to be a few of the secondary electrons and mainly the backscatter electrons. Where you have to go with this is going to depend on your imaging conditions and also the sample, but you just kind of keep turning this negative until your charge goes away and then take an image. Now, if I slow my scan speed down to take a picture of this, you may find that you get charge again, so you might have to use image integration instead of a single slow scan. Just to show that, let me go to another spot that's probably going to charge up worse, over here. Okay, so I need to turn my bias down a little bit more. get rid of the charge there. So now I'm down at like minus 100 and something volts. All right, so I'm not going to worry about this stuff down here, but you can kind of see in the central area I don't have any charge, but that's because I'm scanning with a very fast scan speed. So if I slow my scan speed down, you see I start to pick up charge artifacts in here. So I don't want to take a single slow scan using some really slow scan speed because my image is going to look terrible from that charge buildup. So this is where image integration is really helpful. So instead of doing slow scanning, I can do a fast scan, but if I just do a pause, one frame at fast scan speed looks really awful. So what I do is I go to Scan, Preferences, and I'm going to change my snapshot preset up to one of these really fast scan speeds, like 100 nanoseconds, and I'm going to do integration. Let's just try, I don't know, 16 frames of integration. So now when I hit my snapshot, I get an integrated image of those frames, and it actually looks not too bad. And I would probably do more frames. That seems a little noisy still. So let's click that up to like 64 frames, and maybe turn up my contrast a little bit. And I would say that looks much better. It's a little bit out of focus, but hopefully you get the idea that you can use these detector modes to try to filter some charge out of your image if you have a tough sample. And this way you can try to avoid coating the samples with gold, which I always advocate. I hate our gold coater. If you coat a sample like this with gold, with the resolution of the Nova, if you zoom in like this, all you'll see is the gold film. You'll lose all of the surface detail because it'll just be buried in 20, 30 nanometers of a gold layer. So if I can avoid coating it, I always will. All right, so what we're going to do last here is just going to shut down the microscope and we'll vent the chamber. So now while I have these samples in, if you have any questions that are specific to imaging your material, maybe I can demonstrate something on one of these samples, but otherwise, if you have no questions, let me know and I'll just shut down the system and we'll wrap up today.
I have one question about the carbon contamination. It's form like a coated overlay or something. Does that happen?
Can you say that again? I didn't really hear.
About the carbon contamination.
Yes.
You said one of the symptoms of carbon contamination will be forming a thin overlayer on top of your sample. Is that correct?
Yes.
Yeah. Does that happen during our measurement inside the chamber or sometime?
Yeah. So this sample is pretty clean. I don't really see it contaminating much. Just to show you what it looks like, I can open up the gas injector, the carbon injector, and basically I'm going to flood the chamber with carbon vapor right now, and I'll show you what the contamination looks like.
Okay, so I was just curious about whether that can happen during our sample preparation step. It doesn't happen on that. It just happens during the measurement, right? Inside the chamber.
Right. So the carbon residue is always in the vacuum chamber,
yeah.
But it exists as just like gas molecules floating around.
Okay.
What happens is that when the electron beam hits the sample, the electron beam will cause those carbon molecules to break apart and form a solid carbon buildup on the surface of the sample, but it only happens where the electron beam is imaging.
Okay.
And what the result will be is you'll leave behind these nasty looking black squares on the surface. And as that carbon builds up, it'll completely obscure the small detail you're trying to see. So a clean sample, like this one is pretty clean, you should be able to zoom into fairly high magnification, like this, 150,000x, and I should be able to just sit here and scan on this for minutes. And apart from the drift, which again, I don't know what's going on with that, but you can see that all those little details are not being covered up by anything. So this is a pretty clean SEM, and it's a pretty clean sample. If your sample's dirty, what will happen here? So let me open up the carbon injector. And can you see that the contrast is dropping? Like it's getting darker as it's scanning? So that's the carbon building up on the surface. And what will happen is that if I either scan really long times, or if I limit my scanning to like one small spot here, it'll make this more exaggerated. But what's happening is by building up a carbon layer on this spot, I'm massively distorting what those things look like. And I don't know, can you see that? The little, it's kind of electron transparent. You see like that shell growing up on top of everything? That's the carbon building up. So if I'm trying to measure some of these little tiny particles like these guys over here, if I park the beam on that spot, you're going to have about 3 seconds to get your picture, and then those things are going to be doubled in size by carbon contamination. Or they're going to be just completely covered up with a film of carbon that you can't see through anymore. Right, so now if I look at my whole area, this area is useless. This area is useless because they've been covered up with carbon. There's no way that I know of to remove that. Now I'm going to turn off the gas injector. The carbon material that comes out of the gas injector is designed to pump away fairly quickly. But the contamination from heavy oil, like especially the oil that's on our skin, that will stick around for weeks in the microscope chamber. It's very, very hard to get that out without cleaning things with solvent or using a plasma cleaner. But even that plasma cleaner only does so much. The best remedy is to try to keep the chamber clean as much as possible so that you don't have these types of contamination problems.
Okay, thank you.
Yep. So, but that's what you're looking for is, if you're seeing black marks everywhere where you've imaged, that's a telltale sign that the contamination is in there. Are there any other questions? Oh, so Zhengwei, did you were you watching on the YouTube feed, or did you just join into the Zoom just now? Oh, okay. So to get access to the microscope, he asked a question if you didn't see it. You want to know how to get access to the tool. So after this training is done, I will give all of you daytime access to the Nova, and then you can go into FOM and you can make reservations, and you can come in and use the system as you want for SEM imaging. If you intend to use the Nova for further FIB applications, there will be additional training sessions that we'll host that will go over the FIB-specific components. For instance, like how to make a TEM sample or something like that. But for SEM imaging, by watching this training, you will then be granted access for the Nova. So I will go turn that on right after we're done, and then you can look in our calendar and reserve it. So how to use EDS. I'm not going to cover EDS today. I am going to host a EDS specific training session on YouTube Live on Monday afternoon. Hopefully you saw the email message about that. I sent it to all the current Nova users, and also I believe to all the everyone on the training list. So what I would recommend is watch that video. I will cover how to operate the EDS system, and hopefully that answers all your questions. That one I'm not going to operate on Zoom because I'm anticipating there'll be many people watching it. But there is a chat function in YouTube. You can ask questions through YouTube, or I can answer questions later by email. Do you have any other questions before I vent the microscope?
Can you just repeat what you said about the backscatter mode? You know, you have this like gradient of like lighter to darker parts of the image, and that reflects like the atomic number.
Yeah.
What was the trend with that?
Oh, so higher atomic number materials will appear bright in a backscatter image.
Okay.
So if I'm looking at this surface here right now, if I go to backscatter mode, I'm going to see that there's brighter spots and darker spots. Once I get my focus back. And so the areas that are darker are going to be lower atomic number. In this case, they're carbon. And the areas that are brighter are higher atomic number. And on this sample, that would be platinum. And if I focus better, that'll actually probably show up. Let me check my source tilt. That's good. A lot of times if you're going to do backscatter imaging, it helps to be a little bit higher beam current. Earlier, I was getting a much better signal because I was still at the 2 millimeter working distance. So as you drop your sample away from the lens, it becomes harder and harder to get a nice backscatter image. So if I'm going to do backscatter imaging at this 5 millimeter condition where I'm at now, you can see I don't have a lot of signal anymore. But if I just hop up one beam current, then my image quality improves dramatically at the expense of some resolution. But a lot of times when you're doing this type of imaging, you're looking at larger stuff anyway. And I'm not going to bother with aligning the column right now, just to show you. Now, one thing to be careful of with interpreting backscatter image is that the electron beam, depending on the voltage you're using, has the ability to go completely through the particles and backscatter off what's behind it. So all of this little dusty stuff on this sample is carbon. But the only carbon stuff that appears noticeably darker than the platinum are these thick clusters. The thin little isolated nanoparticles of carbon on this surface are small enough that the 3 kV electron beam is actually able to go right through them, and most of your backscatter contrast is actually coming from the platinum behind them. So if you want to get the true backscatter image on a sample like this, you have to drop your voltage down. So if I take my accelerating voltage down to something like 1.5 kV, and let's see here, get my alignment a little bit closer. We should see a much more representative backscatter image of this sample. As I mentioned a while ago, that when you drop down in voltage like this, you start to throw away a lot of resolution. So we might not be able to see all these little features here, but yeah, we're not really getting enough resolution. But hopefully you can see even through this blurriness that there's a lot more dark material on the surface than there was at 3 kV. And that's because we're getting a lot more representative backscatter signal from those small carbon particles than we did at 3. And if I bring this a little closer, like let's bring it back up to the 2 millimeters. That should increase the resolution a little bit. So focus, stigmatism. This is definitely an image condition that I would go to the Helios for. Trying to image at 1.5 kV on these little particles is not a great idea with the Nova. It just doesn't have the resolution. But you can see there's more black stuff on the surface than there was at the higher voltage. But even some of these little tiny particles in here are still the wrong contrast. So these little guys in here, they're still too small. That even 1.5 kV is too much accelerating voltage to get a backscatter image on those. So when you get down to the like 10 nanometer or smaller nanoparticles, it's really hard to get backscatter images on those things. Just because that electron beam wants to go right through them and scatter off what's behind them. So hopefully, did that answer your question?
Yes, thanks.
Yeah, probably more than you wanted to know. Okay, so if there's any more questions, otherwise we're gonna shut down the tool. Okay, so the shutdown procedure is pretty simple. What we want to do is just make sure that any beams we're using we turn off. If you want to be nice to the next user, I would recommend setting the detector back to secondary electron mode because it's going to start up for the next user in whatever mode you left it in. So they might get a little confused starting out in backscatter mode, but otherwise you can simply click beam on and that'll turn off the electron beam. And then we'll just click vent. Now, when you click vent, the stage is programmed to drop automatically away from the lens. It's really important that you make sure that it drops because if it does not, you risk dragging the sample across the lens when we open the door. Because remember, this is going to move sideways as the door opens. So just double check that it does drop. If it doesn't drop automatically, maybe there's a software bug. You can go in here to the z-axis coordinate and type in the appropriate value to lower the stage. So in this case, because the beam's off, the link turned off between working distance. So now positive is up again. So if I were to type in 0, this would drop. But remember, be careful which way the stage is going. So anyway, I'm going to hit vent, and it's a confirm. And once the chamber starts venting, the stage should drop automatically. Okay, question. When are you planning to schedule FIB? So I don't have it scheduled yet. I will probably be doing that later on in November for FIB training. I actually just noticed this morning that the FIB source on this is actually depleted. So right now, the FIB is actually not usable on the Nova. So I'm going to order a new FIB source and we'll get that hopefully put on in sometime early next week. What you can do in the meantime is I'm doing some FIB specific trainings for the Helios 650 and also the Helios plasma FIB. next week. And I would recommend if you want to watch those will be on YouTube after they're done. They're slightly different microscopes, but the general idea of fib applications is the same. So that would probably help you get a good head start on how to use the fib. Let's see. So once this chamber is vented, which is not quite vented yet, we'll just reach in, we'll take our samples out and close the door and hit the pump button, and then we're all done. Now, just remember, I've had these gloves on now this whole time. I've been touching that keyboard and the mouse, and my gloves are probably dirty again, so I want to change my gloves and put on a clean pair. So I'm going to go do that, and then hopefully the chamber will be vented by the time I'm done. Yep, so chamber's vented. And I got my samples right here. I'm going to loosen the locking cone nut. And then I can go ahead and take out my samples. Now I didn't adjust the stage adapter, but it's always a good idea, just double check that it still fits underneath that 5 millimeter thing, especially if you had to raise it or lower it to get your samples out. And then we'll just go ahead and carefully push the door closed. Now, again, you want to watch that chamber camera view, which you probably can't see it because the webcam view's up, but make sure that everything comes in under the lens, doesn't hit anything, and then we go and hit the pump button. So I click pump, push on the chamber a little bit, make sure it seals up. Everything's good, and now I'm free to log off in FOM, and then we're all done with the session today. With that, if you have any questions, feel free to email me or come talk to me in the lab, or also Bobby is around. He can answer questions about the Nova as well, and I will give all of you access to the system, and then yeah, I hope everything goes well with your experiments. All right, well, have a good day, everyone.
Thank you.